I have no idea why. But the first time I took them off, I was like, what? I had ink on my face.
Oh, oh,
But even
being attacked by his dog. Darwin loves to grab onto Scott's trouser leg and impede his motion.
Chewing on my pant leg. Okay.
Well, my dog and one of the granddogs are snoozing because the two young granddogs were visiting today and keeping them busy. Now I'm down to one young granddog who's out in the backyard.
And your cat might not appreciate that.
I just got news. We're online, by the way.
Oh, we're online.
Yeah.
Okay.
We're missing two.
Yeah, Mike Albro and Abby aren't with us yet. Ivan, I'm glad you could join us today.
Glad to be here.
He was British enthusiastic just a minute ago.
Oh, really?
And I didn't know.
Wow. That's his. That's a very British looking head covering he's got there. Yeah. Let's see. I don't know. Maybe I should call Abby. Mike Albro's kind of hit or miss. He's one of the busiest retired people.
Oops,
oh, there's Abby.
There's Abby.
All right.
Speaking thereof, hi, Abby.
Hey there.
Hi.
How are you?
Doing pretty well.
Great. Well, welcome. Welcome everybody who's viewing us live online. You will be able to see on the YouTube channel a link posted. If you visit that link, you can join us live to ask a question. Alternatively, you can type a question into YouTube using the text chat feature alongside our live stream. And we can take your questions and respond to your comments via YouTube text chat as well. This is Sidewalk Science Online. And let me get to YouTube here. It's hard for me to do more than one thing at a time. I don't know about all you folks. You might be more skilled at that than I am. In any case, we're here with Sidewalk Science Online. This started as an outreach program from Fermilab a long, long time ago. Leon Lederman, the director of Fermilab at the time and a Nobel Prize winner, would set up a table on a street corner and it said, ask a physicist or ask a Nobel Prize winner.
Yeah, and ask a scientist.
Yeah.
And
so we thought that was a good idea. We don't have our Nobel Prizes yet, although I think we're all pretty much in the running.
No.
No? Oh.
I hope not. But my old mentor, Ray Weiss, won it, 3 years ago now, and he calls it a pain in the ass.
Good to know. So in any case, one of our goals is to help spread the wonders of the universe. You know, one of the things that I'm fond of saying is that science teaches us what's real and possible in the world. If you want to know what's true and what you can really do, science is the best formula the human race has ever come up with for understanding that. And yeah, I can hear you, Dave. Oh. We're hearing a voice from above here.
Ooh.
Yeah, here we're getting instruction from our
So the man upstairs.
from the man upstairs.
So we're following directions. Yeah.
All right, I just let Dave know that we can hear him. In any case, so we started that Sidewalk Science outreach, and we may return to that this summer a little bit because we're getting some vaccines in the community, vaccinations and whatnot. But you know, this is an alternative forum for talking about science, and the way we approach it is we spend a few minutes talking about some interesting bit of science news, and then we're going to have a sort of a focused discussion on a topic that science enthusiasts among us here in the panel, and then also people watching, hopefully will find engaging. And this week's focus topic will be led by John Doty, and he's going to talk about the relationship between math and science, specifically physics, which tends to be very mathematical in its formulation and description. And I'm really looking forward to that conversation. I should mention that we're sponsored in part by a grant from the American Humanist Association. We are all humanists. And for us, that means that we believe that science is not only the best way to know what's real and true, it is actually the only way. If you assert that something is true and real, you've got to be able to measure it. You've got to be able to reproduce the phenomena, etc. And so we're
and you have to stand up to rigorous peer review. I mean rigorous.
Yeah.
It may go on for centuries.
Also, there's a certain humility that comes along with science. The idea that we are never 100% certain. There's always room for some new experiment or some new piece of evidence to change our minds. Now, individual human beings, ourselves included, we may find it hard to change our minds once we become convinced of things. I know that I believe any number of things that I've been persuaded about from science, but at least in principle.
And then you figure out I was dead wrong.
That's right. At least in principle, you want to be able to change your mind. And so there's a certain humility.
The most fun is actually discovering that nature is doing something completely different from what you thought.
There you go. Oh.
Well said. Well said. And so
now, if you want fantasy, I can provide fantasy. I write fantasy novels.
Yeah.
So look it up on Amazon and you'll find fantasy. It's absolutely wonderful reading. And it has no truth to it whatsoever.
Yeah, but it's fun.
It's fun.
You know, it's a form of art, and art can be fun. And I'm not saying that science can explain art and all of the things that we appreciate.
But if you want to know what's real,
yeah,
you got to do science.
We're also sponsored by the local chapter of our humanist group. We're based out of suburban Chicagoland, and we're called the Prairie State Humanists. We've got a meetup page. Those of you who know about meetup.com, you can see about our programs and potentially join our conversations live via Zoom if you check out our meetup on Prairie State Humanists meetup page. All right, without further ado,
what's new?
What's new in science? There's going to be a helicopter on another planet launching soon. Isn't that amazing?
Oh, wow. Yeah, an actual helicopter. I mean, Igor Sigorsky is just going berserk, right?
I was thinking it might be fun to fly that drone helicopter thing over to where Spirit, is it the Spirit rover that's got all of its solar panels too dusty to work anymore? Maybe we can fly that over to the and blow off all the dust.
I don't think it has enough range.
Oh, that's too bad. Well, give it a few decades. Maybe it can crawl its way over there. But yeah, that's fantastic news. The launch of a helicopter on another world, and the science we're getting from Mars is just spectacular. And you know, one of the things I wanted to talk about, we may have this as a focus topic when it comes up to my turn to choose a focus topic, but I think it's interesting to speculate about why are we doing this? You know, why are we exploring other planets? What's the benefit to science, much less the benefit to humanity? And I think that'll be a fun thing to talk about in a few weeks when it's my turn to choose a focus topic. But
did you follow this new hypothesis that Mars didn't lose all its water to space?
Yeah. Subterranean.
It's all underground. Yeah.
Well, it's in clay.
Yeah, which would be perfect.
Because you know what happens on Earth is you get your igneous rocks, and they've got feldspar in them, and the water comes down, and it hydrates the feldspar and turns it into clay. And the clay washes off the continents and goes into the oceans. And then you've got plate tectonics, and the ocean floor is constantly being eaten up by the trenches. And then it goes down into the mantle, it gets hot, And that drives the water out of the clay and goes back to being feldspar, and the water comes up through volcanic eruptions, and that recycles the water up to the surface. But Mars doesn't have any plate tectonics.
Right.
So if you make clay,
It's there.
it's forever.
Just sits there. Yeah. Yeah. One of the things, I've got and Joanne has some videos there as well on the Prairie State Humanists website or YouTube channel. We've got a lot of science videos. And one of the things that I've mentioned several times during different discussions is the importance of plate tectonics to very potentially the existence of life on the planet. Certainly the existence of a sustainable ecosystem, a recycling of carbonates and whatnot. So plate tectonics should not be underrated, even though it causes volcanoes and earthquakes and other nasty things.
You get water back, you get carbon dioxide back. You really need them.
Does anybody else have a piece of science news that they'd like to share from this week?
Gosh,
Wait,
we had a boring week.
I did see another article about an alternative explanation for dark energy.
Yes, I read
This
something
one
about it.
involving magnetic forces.
Yes,
And
and I didn't follow it.
Not being an expert, I really don't know what to make of it, other than, it's called dark energy for a reason. We see some measurements that we can't explain. And so we've coined this term dark energy as if there was some kind of energy that's pushing everything apart. But we don't know what this is yet.
right.
That whether it's got something to do with a measurement bias or some particle physics we don't understand.
Which would be the magnetism thing, right?
Yeah,
it's an
well,
interesting-
say magnetism in quotes, because
Right.
this is
It's not.
supposedly a field that behaves like a magnetic field, but it has its origin in the dark matter, and therefore it's a different field. It wouldn't register on a magnetometer.
Right. But I mean, I think it's exciting for physicists today that this is something that we may learn the answer to in just the next few years. Right. At least get some idea of whether this is real, or whether this is a measurement error, or whether there's some new particle physics here. So I think that's it's very exciting.
There's this notion of the dark. What's it called? The dark realm. Star Wars fans may find a particular affinity with that term, but it deals with dark energy and dark matter, which are scientifically plausible hypotheses that could explain some of the phenomena observed in the way that the spin of galaxies work and the way the expansion of the universe seems to be working, apropos to what Ivan was saying about measured rates of expansion. But some theorists have hypothesized that maybe there's a whole dark realm where dark matter has its own properties distinct from the properties of the matter that makes up you and me and stars and elephants and other things. So if dark matter has its own unique set of interactions distinct from the matter that you and I are accustomed to, then that could be dark forces. Again, it's not Darth Vader kind of dark forces, but still fun to think about. And this pseudo-magnetic sort of phenomena is a hypothesized manifestation of one of these hypothesized dark forces, but it's not been measured. They just ran a simulation saying, what if dark matter particles
And the computer says,
had a little bit of repulsive effect among the particles, and maybe it would accelerate the expansion of the universe. So who knows? There's much, much more unknown about the dark realm than there is known.
also the discussion recently on the comet that just went past us.
Oh yeah.
There was a discussion there that this is another extrasolar visitor.
Yeah, Borislav 7 or whatever. his
Yeah,
name
whatever
was.
it is, and that this probably is not from this general solar system, but came from someplace else.
And pristine.
Yeah, and that
Well,
was
it
the
must
thing
have come
about
from
it. It's
someplace else
unpristine.
because it's on a hyperbolic orbit. And so,
It came and
Mhm.
went.
Yeah, and
but-
we'll never
but
see it again. It's
it
five.
did, it does seem like its history is one of seeing very little light before it approached the sun.
Yeah, good way to put it. Thank you, John. That was really eloquently said.
So once again, just when we think we know something, it goes, never mind.
And that talks to the humility of science that we were talking about before. Scientists have a reputation as sort of know-it-all, experts and
Which you
whatnot.
did.
And I think science is one of the best fields of study you can go into to really cultivate a sense of humility, because you're typically proven wrong again and again and
You get good at being wrong.
Well, expect to see a lot more of this from astronomy, because there is in progress an explosion of sky monitoring capability.
Yeah,
Big.
and more
Big
coming
telescope.
online soon.
That's what I'm saying. There's
Big
lots
one.
more coming online.
Yeah, the one that's going up in Chile is just an enormous beast.
First there was a multiple mirror telescope, and then there was the very large telescope, and then there was the even larger telescope, and then there will be the really huge telescope. They're running out of superlative names.
This is even bigger than the last one telescope.
Right. I remember when I was a kid back in the 70s and 80s, Mount Palomar,
Yes.
the
The
giant
200-inch.
200-inch telescope
Wow.
was the telescope in the world for seems like decades, but
It was about a quarter century.
Yeah. And then, boy, has it been surpassed in the past 20 years.
That was an interesting bit of history, because it was very difficult to scale it up further.
Mhm.
And it turned out, after finally, what really showed us that was the wrong way to go for a big telescope was the multi-mirror telescope, where instead of making it really heavy and stiff, you make it very lightweight
Several of
and
them.
you adjust it.
Yeah.
Yeah, the mirrors are actually adjustable.
Yeah, well, it turned out that the adjustment didn't work very well on the MMT. They weren't dynamically adjusting it, but still it worked really well, making it light. The trouble with the Palomar telescope is it's just too heavy.
That's huge.
And the result is that it doesn't cool down to the temperature of the air when you open the dome. It takes all night.
Mhm.
And so a lot of the trick to making these really big telescopes turns out to be temperature control and making them lightweight and thin enough that they equilibrate with the surrounding air fairly quickly.
Cool. Thank you, John. Thank you. All right, John, you're doing a great job of explaining things to us
Great.
today. Let's continue on that theme. Let's have John talk to us for a few minutes about the relationship as he perceives it between mathematics and physics.
Okay. Well, go back 4,000 years.
No problem.
People knew about things like circles. It kind of looks like a circle.
Yep.
Except, well, it's just got some thickness to it and all that. And, another thing that the early folks knew was that they knew that the ratio between the diameter and the circumference was a little bit more than 3. They didn't know just how much, but they did know that it was a little bit more than 3. And, that situation prevailed for quite a long time. And then they started reasoning about other geometric figures, and they sort of came up with ideas that were connected to each other about how things worked. Finally, a bunch of mathematicians that I've got the name Euclid in this piece of paper is quoted because Euclid is a name we stick on a whole school of mathematicians. There wasn't just one person who came up with this stuff. But he got all the credit. Science still works that way sometimes.
Yes.
And he came up with these ideas, what we call Euclid's postulates. And notice that one of them talks about circles, but be careful. He wasn't talking about this. He was talking about an idealized circle that was perfectly rigid and never changed and had no thickness to it and all that. When Euclid talks about a circle, he's talking about a product of the human imagination, because you can't actually produce the object that a Euclidean circle represents. Still, using this stuff, you may prove things. And here's a result that was known before Euclid, but now, because it can be proven using Euclid's postulates, this is a permanent piece of true mathematics. We are certain that this is true, and this will be true forever for the products of imagination that mathematics talks about, triangles and circles and things like that. Go away, Gödel. I'm not going to talk about you today. So that was a tremendous advance in human thought. But it did have a downside in that it convinced people for a long time that reasoning from this kind of thing, which was supposedly self-evident. These are supposed to be self-evident truths. Now, I know that for a fact that many high school students who are shown these things don't consider them self-evident. But, you know, those of us who work with math have been sufficiently propagandized that we do consider them self-evident. In any case, they don't have to be self-evident. As long as we can prove stuff with them, that stuff is true given the postulates. And that worked for mathematics, but it didn't work so well for physics. What are the self-evident postulates of physics? Well, Aristotle thought he knew something about impetus, and you know, it was kind of murky and nobody understood. But then along comes a guy named Kepler, and he has access to a treasure trove of measurements of where planets were as a function of time from Tycho Brahe. And he goes and looks at it, and he's trying to figure out how the planets move. And he's impressed by this guy Copernicus, because Copernicus, said that the planets, excepting the moon, go around the sun, and the Earth goes around the sun. So he had this heliocentric system. And there are regularities in that. One of the things that's nice about that isn't obvious from previous ideas about planetary motion is that Mercury is moving very fast and Venus is moving slower and the Earth is moving slower. But there was this idea that circles are really the thing, and they didn't fit. So he cogitated and he calculated and he came up with a parametric form, and in one of his journals he lamented that the parametric form wasn't an ellipse. It actually was, but he didn't have the analytic geometry to tell. But finally he figured it out and he came up with these. And You could take this as a postulate system, but I defy you to take this as a set of self-evident postulates. This is a set of postulates that were backed out of data. And they work really well for the planets. He then took these postulates and he came up with math, Kepler's equation, and all that stuff. And by that, you can calculate where a planet will be centuries ahead. And it's pretty darn accurate. So this was a really great advance to physics. But it didn't work for the satellites of Jupiter. It didn't work for the moon. And then comes along a guy named Newton. And he, again, let's give Huygens and Leibniz and some other people some credit. Newton wasn't working in a vacuum, but he was doing a really good job of synthesizing what other thinkers were doing. He came up with an idea of universal gravitation and a theory of dynamics. And those theories for the case of a lightweight planet in orbit around a heavyweight sun with nothing else around reproduced Kepler's laws of planetary motion. But they also reproduced the fall of the apple from the tree. They reproduced the moon. They reproduced the moons of Jupiter. And they told you about little tweak. Oh, they also got Halley's Comet right. That was a real advance. But the cost of this advance was something that scared mathematicians. He had to figure out how to measure the slopes of curves. And you can see that here we measure sort of the average slope in this part of the curve with this by seeing how much y changes for an amount of x. But you can see the slope is actually changing between these 2 points. And so you have to, he really needed to know what the slope was at every point along the curve in order to do the calculations he was doing on planetary motion. So he came up with this idea where you replace these deltas with lowercase, we replace them with lowercase d's, just to say that these are really small deltas. These are so teensy that they're disappearing, they're infinitesimal. And now let's suppose that the curve is represented by this equation here, and now we can do this, and it reduces to this. And you notice it's got these dx's in it, but dx is really small. So dx squared is really teensy. So now we take the leap and we replace dx squared with 0.
Yeah, when you square a small number, it becomes smaller. Unlike
That's right.
Large numbers, that become bigger.
That's right. So that gets to be that. And this tells you what the slope of this curve is. And it worked. It got the physics right. It if you measured curves and all that, it got it right. But it scared mathematicians. You can't take a quantity that's not 0 and set it equal to 0. It was so disturbing that the Jesuits, who were very much into mathematics, tried to suppress it.
Wow.
But physicists kept on using it, and it worked, and they were doing stuff, and finally mathematicians started using it too, and kind of worked, and it kind of still scared them, but they kept on doing it. And then there comes along this French physicist who's studying heat flow. And what he says is that you can take let's suppose that here is a function, and this is a really, in 1800, this was not a respectable function because this obeys different rules in different parts of its domain. It's flat on the edges, and then this is 1 minus x squared in the middle. And so first of all, that he asserts this as a function bothered people because a function was a formula. 1 minus x squared was a function. This wasn't. You can't just take a function, chop it up and put on other pieces. But Fourier said, but this is physics. You certainly can have a temperature on a plate, which is the kind of thing he was studying, that follows one rule in one part of the plate and a different rule in a different part of the plate. That's perfectly physical. And then what he did was he broke this thing up into bits that are cosines. And you can see that these are cosine functions. And when you add these 4 cosine functions together, you get a function that's pretty close to the original. And he asserted that if you had an infinite series of these cosines, you could perfectly reproduce this upper function. And then he tried to prove it mathematically, and he fell flat on his face. His math was just terrible, but it worked for physics. And so now the mathematicians are going, okay, these guys. And they started taking it really seriously, and they came up with a bunch of ways to patch up all this crazy stuff that physicists were doing and turn it into something that's called analysis. And I recommend this book. This book is a marvelous historical treatment of it with examples in the ultra-modern program Mathematica. But this is a wonderful book. My son gave it to me. He's a mathematician. He thought I needed it, and it really is a wonderful description of the historical development of real analysis. And what I really like about it is that he talks about the dead ends and, oh, this idea didn't work and this idea didn't work. But if we take this as a postulate, then we can get this, and then that works, and yeah. And mathematicians made calculus and Fourier analysis respectable math, finally. But of course, physicists had figured it out, and we didn't care whether it was respectable math because all we cared about was that we got the right answer. Because we looked at the sky, and Fourier used thermometers and things like that. He did experiments in the lab, and that's what matters to a physicist. You don't care whether the math is actually respectable math. You care about whether it works. Here's another example of a fine equation. Oh, let me. I've got another demonstration first. This is respectable scientific tea leaf reading here. You can see the tea leaves circulating around in the glass of water. And it turns out that there's an equation that describes this. It's called the Navier-Stokes equation. And it comes in different versions for different situations, but this is the version that applies to a glass of water.
It's all Greek to me, John.
Yeah, it is. It's very abstract. It's mathematics. But if you're into this stuff, it is a simple and elegant equation. I will again say that you do have to be into the mathematical propaganda to see simplicity and elegance in math often. But it actually breaks the motion up into bits. This part just tells you how it's changing in time. This little bit here is about the fact that the features in the flow themselves are carried along with the flow. This is about friction. This is about viscosity. And this, for this problem, I just show it for the glass of water. This just reflects the effect of gravity. So it's pretty simple, really. It breaks the phenomenon up into pieces and all that. And it's elegant and it's impossible to solve.
Literally.
And yet it's actually quite useful now that we have supercomputers, because you can get an approximate numerical solution to this by dividing this water that, in your abstraction, you divide this water up into 1 billion little cells, and then you do calculus in reverse. Instead of these dells are representative of the little d's of single variable calculus.
Those are the upside down triangles.
So what you do is you run calculus backwards. Instead of deducing the slope at a point, which is what this Navier-Stokes equation wants, you say, okay, I'm going to represent the slope at a point by the average slope across one of these little cells. Okay, so it's called finite element method. And if you divide this up into 1 billion cells and put it into a supercomputer, you can get the motion quite nicely. And this is very useful, actually. If you fly on a modern airliner, the wings were designed that way, using the Navier-Stokes equation. Because you can't learn everything about the flow from scale models in a wind tunnel. You can learn different things from the Navier, from a simulation using Navier-Stokes. But this is also a case where the mathematicians don't quite get it. You can win $1 million for a mathematical characterization of the solutions to the Navier-Stokes equation. But notice that it talks about smooth. But physically, it actually isn't smooth. If you look at this close enough, it's made of molecules. It's not a smooth fluid. And in fact, you don't have to look that close. If I just had a microscope and suspended some micrometer-sized particles, which are still 1,000 times bigger than a molecule, you would see them jiggling around in the fluid in a way that Navier-Stokes doesn't predict. We call this Brownian motion. It's a consequence of the fact that a small particle is constantly getting bashed around by the molecules. And so this kind of misses the point. What we want from Navier-Stokes is approximate solutions that match reality, not exact solutions of the sort that a mathematician likes.
John, could you mention the name of that book you referred to again? I'll put it in the chat.
Okay. It is A Radical Approach to Real Analysis. And it's by David Bressoud, B-R-E-S-S-O-U-D.
Thank you.
And I think it's a wonderful math book. And then there are other things that are funky about mathematics. One consequence of this work was that ideas of functions and objects and all that wandered off into a land of abstraction, where Euclid's ideas have some really bizarre consequences. To Euclid, a point has no dimensions. Now, in physics, we don't know of anything which is actually a point. We talk about electrons as if they were point particles, but in fact, they really do have finite extent. And, if you do the quantum field theory, they're dressed with bunches of stuff around them. And there really isn't a point in there. To the extent that we think there is, it causes us mathematical trouble. But anyway, points are tricky things. And so in the 20th century, but mathematicians like to take Euclid very seriously. So in the 20th century, they came up with something called the Banach-Tarski construction, which I have this fine comic XKCD about. I carved and carved, and next thing I knew I had 2 pumpkins.
Oh, right.
Because in the Banach-Tarski construction, it is possible to take a ball considered as a set of points, cut it into pieces, and then reassemble the pieces into 2 identical copies of the first ball.
Exactly the same size.
Exactly the same size.
Each of them. Yeah.
Because it's made of an infinite number of points. And points have no volume, and so the volume that we would think
or area, right,
isn't conserved by these slices. And so mathematics goes off into Never Land, which is fun, but maybe not terribly applicable to real life. And sometimes some physicists get a little bit lost in this. I have seen the sort of, there are physicists who claim that all physics is just mathematics.
Some claim that reality is mathematics.
Yes, I know. And I've seen that, I've seen a couple of that ilk say, oh, we should banish Newton's idea of force from physics, because it really doesn't work in the more abstract physics that we deal, the more abstract mathematical physics we deal in. In general relativity, there really isn't a gravitational force. In quantum field theory, the changes in momentum by interactions are more akin to refraction than they are to pushing and pulling. And I say, I'm an experimenter through and through, and I say no, because one of the simplest things I know of to explore physics is a force gauge. I can take my little ring here, which is elastic, and I can measure how much I'm distorting it. Use a ruler here. I can measure how much I'm distorting it by pressing on it. And that's a force gauge. It's one of the simplest physical instruments to make. And I am of the opinion that that really is the foundation of physics, is simple measurements that you can make, that you can then concatenate together and pile up and do more complicated measurements and more subtle measurements. And you can, find the mass of individual atoms, and you can measure the momentum of individual photons and stuff like that. But it starts with things like this. And I don't think you can really connect this very easily to quantum field theory.
Interesting.
So I end with that experimenter's opinion of the idea that physics is mathematics. I think that the physics that we actually use in the lab and that we experience as human beings, it has a much more subtle and contingent connection to the mathematics than the idea that, mathematics is, reality is mathematics. So that's an opinion. And that's the end of my talk.
Wow, excellent. Thank you so much. That was really illuminating. Appreciate it. Well, let's first open it up to our panelists. That would be ourselves, and then Ivan and Abby. Let's start, Abby, with you. Did you have any insights or questions?
Well, I noticed one really beautiful thing that John did there very early on. It may have even slipped by his notice. He was so busy telling us cool stuff. Very early on, for physics, when you were saying that, you know, the math was inelegant, but physicists did it because it worked. And so it did that thing which science has to do. Getting back to this again, it made successful predictions. If they used that math, no matter how much the mathematicians didn't like it, if they used it, it made predictions that they could then test, and the predictions worked out. So it kind of passes the smell test for science, even if mathematicians don't like the math.
Yeah, I like the idea that physics is science. It's not mathematics. Mathematics has a quality of pureness, which also has a quality of fantasy. Now, I can understand fantasy, but physics, and chemistry, and biology are real.
The thing that's different about mathematics from literary fantasy is that mathematics puts the objects of the fantasy within a box of reasoning where you can know precisely what the nature of those objects are in certain measures and characteristics.
And in relation to one another.
But you're right, it is fantasy. There's no such thing as a circle. I can, I've got a thing that kind of looks like a circle here, and I've now dropped it into the bottom of my box. But
it's circular.
It's circular if you don't look at it under a microscope, or actually even close. If I take my glasses off and look at it close, I can see all sorts of little bumps and stuff on it.
An approximation of a
it's an approximation, and everything in reality is an approximation of the mathematical objects that we use as models of that reality. And a very large part of what we do in physics is probing the limits of those approximations.
Yeah.
Ivan, did you have a insight or question?
I'm still thinking about it.
Okay.
I mean, I agree, and I think that this is a little off topic, but it reminds me that I was always interested in science. I always wanted to be a scientist and an astronaut when I was a kid, and I knew I needed mathematics, so I worked on mathematics, but I didn't really enjoy it until I got to calculus, and that was because I had done physics and I had looked at problems and I thought, I need to know what the slope is at every point on this curve, or else I won't get the right answer. I'll just have some horrible approximation, and this disgusts me. and then I learned calculus, and I'm like, I know what that's for. I can use that.
Yeah.
I agree that if you use calculus to solve a physics problem and you do the measurement and you get the right answer, you're onto something, right? You're onto something. But I'm also a little hesitant to dismiss what the mathematicians are doing.
I pay attention to what the mathematicians are doing. That's right. Why I think this book I held up is so fascinating.
Right.
But
it's possible
there are constructions in here which make no physical sense. But there are others that do, and it's important to know this stuff.
Yes.
Well, I'd raise a couple of points that I know about, and then I'm going to ask a question that was posted on our YouTube channel in response. So my thoughts are turning to two examples in physics where the mathematics maybe even three, three, where the mathematics really led, just because of deductive reasoning, led to physical discoveries. So I'll name the three without going into detail. We probably don't have enough time to get into all three. One is Dirac's formulation of the way that particles propagate through space-time. And he noticed that as a consequence of Einstein's relativity theory, one should treat time and space on equal footing. So he tried to take what some of you've heard about, at least something called the Schrodinger equation. Dirac took the Schrodinger equation and tried to come up with a representation of quantum waves that did treat space and time on absolutely equal footing. And when he did that, the mathematics predicted antiparticles. And so just mathematical deduction there led to the prediction of antiparticles. The second example is the potential field in electromagnetic theory. There's this, it's often represented by this symbol A in equations of electromagnetism. It's this convenient mathematical construct that talks about a region of space where there's no detectable independent magnetic effect or electrical effect, but there's still a potential field. Well, that was a nice mathematical shortcut that allowed people to use Maxwell's equations. But when quantum mechanics came along, they found that that mathematical convenience had implications for the way that quantum mechanical waves representing the measurable qualities of a particle should be affected by this mathematical fantasy called the potential field. And that turned out to be true. And then the third and final example I'll raise is Einstein's general relativity, where he treats space-time and the geometry of space-time as ideally, not Euclidean necessarily, but as ideally smooth geometry without any granularity or discontinuities, black holes accepted in some way. But in any case, this prediction and this set of mathematical deductions about the geometric properties of space-time, which assumed perfect, smooth, continuous, mathematically elegant forms, does seem to bear up under scrutiny. So these are three examples I can think of where the mathematics deployed in the service of explaining physical theories has led to discoveries and further explorations, just because the mathematical form seems to be so predictive and consequential.
Well, let me comment on that. It is absolutely true that when you choose the right mathematical object to for a physical model, the properties of that mathematical object often turn out to make predictions that you weren't expecting. But to call it deduction is a little bit of a stretch.
Okay.
Dirac's theory was one of several. It's the one that happened to work. But it wasn't like there was some set of postulates that you could do that would lead to a correct theory. In fact, there was something called canonical quantization, which Dirac also helped create, which was a way to take classical systems and deduce what the corresponding quantum system would be. But it only sometimes works. And the electron is a case where it doesn't work. And Dirac had to come up with a more elaborate theory that included spin, and then the theory that incorporated spin turned out to predict antiparticles, and that was the great thing. But canonical quantization is an axiomatic, Euclidean type deductive approach, but it doesn't always work.
Okay.
Sometimes it does, and then you use it and you'd say, this is good.
And I don't know if it's historically accurate, but the story I have in my head for Dirac is that okay, you have an electron in his system. Well, there's nothing to stop it from decaying down to lower energy levels.
Yes.
Unless those energy levels are already filled by an infinitely deep sea of electrons.
Yes.
And what he noticed is that the holes in that electron sea behave just like electrons with the opposite charge.
Yes.
So I don't know how.
And then he, for a while, he was trying to contrive his theory so that they would actually behave like protons, but that didn't work.
Mm.
So yeah, so I don't know how purely mathematical it is to say, well, we'll just say all those energy levels are filled.
Okay.
Because, I mean, everybody knew it wasn't realistic anyway, that, I mean, it would have infinite charge and infinite mass. But it did work.
Yep.
Okay.
I think what nailed it down was that people looking at cosmic rays and cloud chambers started noticing particles that turned the wrong way.
Mm-hmm.
The funny thing is they'd photographed these before Dirac, but they hadn't noticed that they turned the wrong way until Dirac came up with the idea.
Yeah, cloud chambers.
Oh yeah, some of these are going the wrong way.
Oops. We have a question online, and we can get back to this point about the mathematics here of some physical theories in a second. But I want to make sure we get to this question. James, who's viewing us live, says, what do you think of the perspective for biology that explanations are primarily in the form of processes, not determinism in mathematics? Process, in this case, and processes are no less real than physical mathematical representations, I assume is what he's saying. So I don't know, in biology, I know that sometimes when you're simulating population dynamics and, the flow of blood in capillary systems and so on and so forth, there are times when using mathematics in the description of a biological system or an ecological system is relevant. But, I don't think biology ever really gets to the point of quantum mechanics, unless we're talking, maybe if we're talking about something like the interaction of particular molecules. I don't know for certain, but it may be that quantum mechanics.
If you've ever read some of the literature on evolutionary dynamics,
yeah,
it's as difficult as quantum mechanics.
Okay.
I leave that stuff to Abby.
Yeah, Abby, do you have an opinion about?
There is quite a mathematical theory, connects to dynamical system theory in physics of evolutionary dynamics. And one of the nice things for me is that it shatters all the naive ideas of neo-Darwinism, that it's just, gradual natural selection and all that. In the mathematical theory, drift has a huge effect. Isolation of populations and exchange have huge effects. There are jumps, there are discontinuities. It's all like real life.
Fits and starts.
Yeah.
Abby, do you have some thoughts about the relationship of mathematics and biology?
Well, a lot of people have tried a lot of things, and they sometimes work. It can be really useful even for interesting things like, mapping the airflow of air through the hole of a prairie dog. Turns out those are better arranged than you might think. So there are things certainly that we can use math for, in terms of how sunlight hits the leaves on a tree. Cool stuff you can do that can actually be a helpful tool. And likewise, of course, biologists, when you start getting into populations or for that matter, drug tests and this kind of thing. We just love statistics.
Yeah.
I'm a little bit caught up can you repeat what you said about processes versus mathematics? I'm not even sure I quite understood what that was getting at.
Yeah, James says, what do you think of the perspective for biology that explanations are primarily in the form of processes, not determinism and mathematics?
I'm not quite sure I really understand the question, to be honest.
Yeah, I know that there's this thing called systems thinking and systems biology.
Mhm.
And if I remember correctly, it has a lot to do with interactions and processes, causes and effects and things like that. And it tries to look at things systemically as a set of processes. But, I don't know, in general, I don't really know a good answer to the question, but what I can throw out there is if it's something you can measure and quantify, right? If you can quantify the number of species in a given plot of land, if you can quantify the rate of population, growth and death, if you can quantify the amount of air and flowing in and out of the holes in a prairie dog village, if you can quantify it and measure it, people will likely look for some mathematical way to build a model of that system.
Mm-hmm.
And that takes me to a larger point, which I'm pretty passionate about, and that is the human endeavor of science is largely an attempt to create models that we can use to understand the universe. To truly comprehend the universe, we'd have to conceive of all of its pieces and machinations at the same time. And it's much more prudent to try and create models of bits of the universe. And if it's quantifiable and measurable, then mathematics immediately lends itself to that endeavor.
I should also point out that a lot of the mathematics that we use for the analysis of statistical data actually had its origins in social science.
Mm-hmm.
Yes.
Now, I'm talking now about frequentists, not Bayesians, Ivan. But
Yeah,
yes,
in biology,
regression analysis and things like t-tests and all that stuff started out as in social science and is very heavily important in biostatistics.
And actuarial tables and
Yeah.
the insurance industry.
My wife is an epidemiologist, and she is really into biostatistics.
Right. In fact, I was going to say that, I've certainly seen papers, even whole books about that basically are just equations that predict what animal behavior, what animals ought to do, whether they do or not, and things like that. But to a much larger degree, in biology, when you do math, it's the kind of math that has numbers in it.
Yeah. And
Yeah.
again, in my work also, it's all statistics. That's the furthest we ever go in our mathematics. All these delta thingies and everything else are really cool, but we don't use them.
Population statistics.
Yeah, it's what happens when a whole group of people do this and then they do that, and then we're looking at massive numbers, and then we try to predict the individual, and we discover no, it doesn't work at all.
Well, all these delta things are
almost back to Brownian movement, that the individual is moving their own way, but there's a mass of water going around that glass of yours, and we can see it as a mass, but you can't see the individual atoms, which are just sort of bouncing around, having a grand time all by themselves.
Well, all these delta things are insightful, but they're actually very difficult to use. One of the things another thing that convinces me that reality really isn't mathematical is that if you assemble the components of a small molecule, it figures out what its shape is in a few picoseconds. It takes you hours of supercomputer time to figure that out.
That's almost directly related to a question we've got online about, do you think math can sometimes slow down the science? Doesn't experimenting give us faster results? Well, obviously, looking at a glass of water, one of my favorite, I wish I had the demonstration here. There's this idea of you get a bunch of straws that are of different length, and your goal is to sort them. Well, what you can do is you can take them all in your hand and you can put them on a flat surface, and you've immediately sorted all of those straws.
Yeah, done.
But if you had, let's say, 200 straws, thin little straws in your hand, trying to get a computer to do that, well, computers are fast these days, but that's a relatively time-consuming process for a computer.
Over there, I have a very fast computer that I put together to do circuit simulations for my instrument development work. And it's very useful and it gives me insights. And over there is the solder bench where I hook together things and try them out. Mm-hmm. Because sometimes the real stuff doesn't do what the simulation says. And sometimes it's just faster to hook things together and see what they do.
Yeah.
And the whole thing, all of science began with observation and testing.
Right.
Yes.
And then we try to come and make a bigger picture. Say, is this true in general? Can we make a statement that says, if this occurs, that it's always going to go to this extreme or that extreme? And that's where the math comes in.
I want to say as a Bayesian, like in order to have an explanation, your theory has to say how likely it is that you will see certain kinds of evidence, at least in comparison with some null hypothesis, some alternative, right? So you can have a qualitative theory, right? As long as you say, look, in my theory, I can't predict exactly how frequently this will occur, but I think it will happen at least 50% less of the time.
Than something else.
Or let's say, I just threw out the 50% as a random number. I'm just saying enough less than what I would think by default or from the null hypothesis. And you know that from the process that means that you will only very, very rarely see this in the null hypothesis, but you will definitely see it in your qualitative theory. So sometimes you can make a scientific inference without knowing what those percentages are, without having a nice analytic formula. But you still need to be able to say that the probability of seeing this evidence is higher or lower than your null hypothesis given your theory. So you need at least that much structure to your theory to be able to make the inference to your theory from the evidence.
Yeah.
You got to have a structure.
I remember, John was talking about his circuits. I remember as an undergraduate physics student coming across a formula for predicting the frequency with which an electronic circuit oscillates. And, you can put an inductor, a capacitor, and a resistor in a certain configuration, and it will start oscillating. And those oscillations will correspond to emitting electromagnetic rays. And one of the fun things to do was for me to think about what kind of capacitor, resistor, and inductor would I need in order to oscillate such that it emitted light, visible light, right? And, it's a simple equation. The equation is really straightforward. It's a high school level equation. And you can plug in the numbers and say, if I want 2 gigahertz light, what do my capacitor and inductor values have to be? And you can come up with real answers. But of course, that never works. We don't make light that way. And one of the reasons is because the mathematics undergirding that particular description of a circuit has all kinds of assumptions about the purity of the oscillator and the purity of the inductor and the purity of the resistor. And when you start, driving things with such at such frequencies and such extremes, an inductive coil starts having a little bit of capacitance, and the capacitor starts having a little induction, and the resistor starts having a little induction, et cetera, et cetera. So reality is messier than some of the mathematical models. And I think that's probably what, John, you leverage when you're at your circuit bench. You know how some of these components work.
Yeah.
And you have so much experience with them that you know that if I put one of these along with one of these, I'm likely to, you know, exceed the tolerance of this or not exceed the tolerance of this other thing, etc. So your intuition about physical reality trumps your mathematical simulation in some cases.
It does. And then, you know, I've also done chip design. And there it gets really hard because you can't actually go to the bench and build a fragment of a chip. You really do have to simulate it.
Yeah.
And then you send it for layout, and the layout people come back and they have an abstract representation of your circuit in terms of a circuit that represents all those little capacitances and inductances and resistances that you're talking about. And so you wind up doing a comparison between what you intended in one simulation, which is the things you wrote down, and then this other simulation that was extracted from the pattern that you're going to do photolithography on. And it's extremely slow because the layout-based circuit is 100 times the complexity of the thing that you drew.
Yeah. We have a question on YouTube. John wants to know what kind of software are you using to do your circuit simulations? I don't know if that's something you can talk about or.
I use ngSpice, which is an open source circuit simulator. And I use Lepton EDA to draw the circuits.
Thank you.
That's another open source thing. I used to use commercial stuff, but it's expensive. And the problem is it's not very suitable for somebody who does a lot of different things and also has very intermittent income, because the idea is that you're going to spend $50,000 a year for an engineer's seat who just sits there 24 hours or whatever, 8 hours a day, doing circuit simulations. Well, I don't do that. I'm a physicist and I do all kinds of other stuff in addition to circuits. And so the free stuff is really good. And actually the extraction from Lepton schematics to something that you can simulate with ngSpice is something that I wrote. And it's part of the Lepton distribution now. So I do some software too.
Thank you. So we've got a couple people that are really interested in the sort of the biology take on things. Thinking about some of the processes. When Charles Darwin came up with his theory of natural selection, I don't think there are any equations in his theory, but his theory is considered one of the greatest scientific theories in all of science.
He did have a diagram.
He did have like the tree of life kind of diagram. And when we talk about things like phenomena and processes in biology, about pressure, right? We talk about evolutionary pressure. Well, it's not nearly the same thing that physicists mean when they say pressure, which is force per unit area.
Totally different.
Right. So I think that sometimes the way that we use language in our descriptions of science, not to mention the term theory in of itself, which is confusing to lots of people, but the way we use language in our descriptions of science can kind of muddy the waters when you're trying to understand it. When we talk about evolutionary pressure to change, if you're a structural engineer, well, you have a pretty clear idea of what pressure means, but that's a very different kind of pressure. When we talk about energy, today I have high energy. Yesterday I had really low energy.
And what does that mean?
Yeah, what does that mean? So
you got that from physics. Physicists invented the
right.
word.
Yeah.
Right.
But one of the things that we have to balance is, on the one hand, it's confusing to use the same words or similar words to mean a variety of different things. On the other hand, if we make up a special word for every single phenomenon, it becomes just as confusing, if not more, and far more, in fact.
Yeah,
it's a balancing act, and it produces odd things. And I remember being in a meeting with the Japanese Space Agency and NASA, and they had simultaneous translation, UN style, because the Japanese engineers weren't real good at English and the US engineers were no good at all with Japanese. But I can read Japanese, and so I was sitting and listening to the translation while reading the slides, and I almost cracked up because the translators got lost in the maze of words that refer to pressure and mass and gravity and weight. They're all the same Chinese root. And so they were talking about gravity control when we were really discussing the mass budget for the satellite. But
wow, interesting. One of the things, back on the topic of evolution, one of the things that I try to be careful about or conscientious about is people use the word design. Like a duck's bill is designed to make its way through seaweed or pond scum and get to little fishies and whatnot. And the duck's foot is designed with webbing to propel it through the water. And the whole argument about design versus evolution has become so fraught and poisonous for some people that I try very consciously to always use the term has evolved to, right? The duck's bill has evolved to do the following.
The duck's bill is adapted to do by.
Right. That's another way to say it. So
to be pretty good at doing this. Right.
There you go. Right.
Much better than these.
Right. So, we tend to use sloppy language sometimes, and I see the same thing in science journalism. I don't have access to a lot of actual science journals because they're very expensive for an individual. But, the science journalism I read about, where reporters talk about science, especially in the realm of biology, I will see occasionally these shortcut terms like design and its purposes and whatnot. And those are always concerning bits of terminology when really it's phenomenological. Back to the original question that was asked half an hour ago, that it's about processes and phenomena and the consequences of those processes and our extrapolations. But it's really hard to wrap those around mathematical formalism a lot of times.
When you get to chemistry, yes, we have an awful lot of mathematics. When we get into vibration, again, and this goes through the course of the physics side of it, when we begin to talk about spectroscopy and those kinds of things, we're dealing in energies and we're looking at energy spectra. And can you use an awful lot of mathematics to describe it? And yes, of course you can, because it's a wonderful physics phenomenon.
Vibration.
But do we? And the answer is no. When you look at an infrared spectrum, you don't care really that it's actually at 2271, and this is at 2272. No, you're looking at the overall function, saying, oh, that's a carboxylic acid. That's a ketone. There's an aromatic ring. That's chlorine.
Their
and you're looking
at,
so you're basically looking at fingerprints. And similar when we get into the area of mass spectrometry, where you are dealing with the mass of atoms. Do we really count them all out, or are we looking at general things? Are we looking at carbon-12 versus carbon-13 ratio? Are we looking at oxygen ratios? Again, what kind of ratios are we talking about? And then making the extrapolation out and saying, oh, this is a molecule which is this big, which has an oxygen over here, and it's actually, and so forth. So most of this stuff, even in chemistry, we don't deal in the mathematics of the physics. We're looking at this in terms of a tool for identification, and we're looking at general principles. Can we go about the other way? Yes. Is it long and involved and tedious? Yes. Does it accomplish the job? No. So we let the physicists have that kind of fun. That's their fun. So in chemistry, we don't deal with these numbers at all. They just happen to exist and we're using them.
Yeah.
And we find the same thing true in biology, I think. And I know, again, in my work in memory and the utilization of knowledge and critical thinking, that, again, common statistics is all I ever used. I don't really care what the synapses are doing.
Mhm.
I'm looking at the overall effect. Can I train a person to do a job? And will they do it better after training than they did before training? And that's statistics. That's nothing to do with anything.
Back in the, I guess, early 1900s, a famous physicist, Ernest Rutherford, made a comment that I think has been, it unfairly denigrates certain fields of inquiry in the sciences. And he said something like, all science is either physics or it's stamp collecting. And
I don't agree at all.
yeah, I don't agree with that either. He won a Nobel Prize, though.
but not for
Yeah,
that.
he won a Nobel Prize for the result of an experiment he told his students not to do.
Yeah.
Yes. Yes.
And they went ahead and did it anyway, and then he won the prize for it.
Yeah. Well, that was like, what's the famous experiment about sending electricity through nitrogen gas and whatnot? Not Fleischmann Pons, they were the cold fusion people. I'm drawing a blank on their name, and I know it well.
Mhm.
And
Yuri,
Yeah.
Yes, Yuri.
Mhm.
Are you talking about the Miller experiment?
Yeah,
Yes.
Yuri Miller experiment. Yeah, one of them was the advisor to a graduate student. I think it was, I don't remember which is which.
Miller's graduate advisor. Miller actually ran the experiment. He was the grad student who ran the experiment.
Yeah, and Yuri gets,
Okay.
half the credit for it, but he actually said, I don't think you're going to find anything. This isn't worth doing. But in any case, this idea that, if it's not physics, and I assume by that he meant essentially mathematical physics, then it's stamp collecting. And there's a great virtue in stamp collecting. I mean, look at all the specimens that Darwin and Wallace and other biologists have collected. It helps them piece together the story of life on our planet. Joanne, in a couple months, you want to talk about Tiktaalik. And that was a wonderful piece of stamp collecting where somebody said, I bet I can find this particular fossil in this particular geologic era.
Well, again, that was an accident. Oh, look at this. What is this?
Well, they went looking for that.
Oh, yeah. Well, yeah.
Actually being brave and making a prediction.
Yeah. Yeah. So I don't, there are people out in the world, I'm not going to name any names. Some of them have written some books that are fairly accessible and readable about this hypothesis that reality is at root mathematics. And I don't know. I'm not yet persuaded by that.
No.
There's another similar line of thinking that reality is really just information. That when you look at the state of a fundamental particle, and everything is really composed of fundamental particles and fields, all you're really talking about is the information content of that particle. So maybe at the root, the universe is information. I don't know. I'm not persuaded.
Reality. I mean, people will say things like, "Oh, DNA is like information." That doesn't mean it's the same as
Right.
information, computer code or this kind of thing. Yeah, looked at from a distance, you can see that there are some similarities, but there's a huge difference between the word like and the words is the same as.
I really enjoyed Max Tegmark's book, Our Mathematical Universe, in which he describes the different levels of multiverse that might exist. And the fourth level of multiverse, which is sort of, I think, his contribution is, or at least one of his contributions is this idea that if we look at the relationships between things in our universe described mathematically, there's nothing in there that makes something real per se. Like like when we're making measurements, we're looking at ratios of things. Like we're looking at mass, we're comparing the mass of an object to the mass of a proton, right? We have to choose some units. And so in that respect, the things that we measure are very much like things in mathematics where you just have ratios. And so he has this idea that, well, what if the universe, like the mathematics is the universe, and if our universe has this mathematics, well, every mathematical system exists in the mathematical sense. In the mathematical sense of existence, it's just, can I put these postulates together and create a system? So if that's true, then every mathematical system that could describe a universe exists, and therefore you have a new multiverse in which you have all the possible universes. And I thought that this was actually a very charming idea, but I did not agree with his argument for why it's actually true. Which is, he says, if it were not true, then why is mathematics so good at describing universes? And my answer would be, because mathematics would be useful for describing any consistent system, even if there's only one of them.
Mhm.
But I did find the idea very elegant.
Yeah,
Like, I found it charming, but like not.
Mathematics is a wonderful tool, but the tool is not the object that the tool creates.
right. Yeah, I think probably all of us here on the panel today agree about that. But then we don't have a theoretical physicist, a practicing hardcore theoretical physicist to propose an alternative point of view. But that point of view does exist. I will tell our audience that there are serious, deep thinkers who are persuaded of the validity of the notion that mathematics is really the root of the blossoming of the physical universe, and that in principle there should be a purely mathematical description of reality that yields consistent predictions and physically measurable outcomes. But as John mentioned, back in the era of the Greeks, when they wanted the solar system to be represented by perfect spheres, or in the Middle Ages when they had the Platonic solids, the cube and the sphere and the dodecahedron and whatnot. All of those ideas were mathematically very elegant, but they turned out just not to do a good job at describing reality. So I recognize that a lot of people still are persuaded in the value of thinking that way, but using Bayesian sorts of reasoning about the track record of pure mathematical reasoning, I'd say that I don't know, the jury's still out, at least.
The other problem with that track record is, as the theories get more and more abstract and mathematical, it becomes harder and harder to connect them to the real world.
And the real world is complex enough. I mean, the moment you get into biology and sociology and those kinds of things, you lose track of all the finite data. It becomes mass data.
The poster child here is string theory, which has taken over whole physics departments and has not yet produced a testable prediction.
Right. Yeah. Well, we need to wrap up for today. We're at our hour-and-a-half mark. It's been a really delightful discussion. We can return to this topic in the future if there's appetite for it. We'll be back in 2 weeks. We'll have a new topic. Again, check out the meetup page for Trary State Humanists, and we'll publish what our next focus topic is going to be there. We'll be seeing you again in 2 weeks. Thank you so much for joining us today. Thank you to our panelists. Thank you, John, for an excellent topic, food for thought.
Ivan, Abby, great to see you again.
Take care.
Thank you for doing this. This was nice.
This is fun.
Bye-bye.
Bye, everyone.
Thanks.